Okay, I just want you to note the way things are happening because we did have a little bit of lead-in time with this test, so it was a little bit of, we had a couple of weeks in there that I call like getting settled in time, but we do not have that time from now on. So what's going to happen to you is test 2 is going to come right after we cover chapter 3 this week, chapter 4 next week, then you'll take a test. Then we will do chapter 6, chapter 7, and take a test, okay? They're going to come a little faster. Now, I tried to put a little more time. If I have a choice of where to put time in a semester, I'm going to shove it into the back, the very end, because this is the hardest material that we have to cover down here. We finished today. Some of you are going to question that because this is confusing stuff that we're covering today. But basically, the hardest material comes at the end of this class, okay? Tests get progressively more difficult, so you might want to schedule your study time accordingly, your ASC time, and come and see me in my virtual office hours on Tuesday evening and Sunday evening, 5:30 to 8 on both of those. All you have to do is pop in. I'm sitting there, okay? So you can come in and talk to me then. Now, I know you've already covered this in the lecture, so I'm going to hit some problems real quick and just remind you of some things. I'm not teaching it. Remember, the teaching goes into your video lectures that are inside. You guys are hybrid. So you should have already watched chapter 3 lecture, so that's why we can cover some material very quickly today. If you have not, then expect to be thoroughly confused until you go back and watch that lecture, okay? Don't watch it, work the pages in it, be diligent in that. Some of you will need to do it twice. We have a sample of students. They're asked if they own a pet or not. This is called a contingency table. And a contingency table asks more than one question of some survey participants. In this case, it asks, do you own a pet or not, and are you male or female? And it captured that combination of answers. So when we put it in this table like this, we also need to consider that we have totals that they never give us, and we have to come up with those totals. In the interest of time, I'm going to give you the totals. But when you're adding them yourself, you add the rows across, you add the columns up and down, and then you do the sums of the totals. Double check yourself. This 150 over here should be the total number of people surveyed, okay? If it isn't, you've got some of your totals wrong. There's really no sense in starting to answer probability questions unless you get these totals right, okay? So it's worth a little double check when you're adding them. Now it asks us this question. Suppose one student is randomly selected from this group of 150, and that's always the way these questions go. I mean, we're saying probability is always based on what if I choose one randomly out of this group? What is the probability that that student is female? Now that is a single condition, okay? That's a single probability. We call these marginal. Hopefully you're remembering this from the lectures. Marginal probabilities only look at one thing, whether it's female, whether it owns a pet. Those two are marginal probabilities, okay? And they're simple. Embrace the fractions, guys. Probabilities are fractions. I know you hate fractions. You have avoided them. You would rather go to decimals, but be careful. Don't go to decimals too quickly in probability or you'll lose the precision and you'll miss the problem, okay? So just get used to these fractions. They're going to be your friends when we're doing probability. So what I'm going to say is, when I'm dealing with a marginal probability, the question is how many are female out of the total 150, right? So out of the total 150 says, how many are female out of the total divided by 150, over 150, however you want to think about it. And then you look up here, where's the number that's female? If it is marginal, the only numbers you're going to use are in the total row and the total column. Those are the margins. You won't pick up anything in what I call these interior cells. Only look for the margins. So where are the females? Well, there's 60 of them. And then you can easily do that division. I wouldn't even do it for you, but round to 3 decimal places, you should get 0.4. If you question how your calculator is doing things, then practice later, okay? Next, what's the probability that I select one and that person owns a pet? Well, once again, it's a marginal probability. It's over the 150 total, isn't it? And how many own a pet? Well, the total that own a pet is right here. Own a pet, total, 91. When I do that, If I round to 3 decimal places, I get 0.607. Once again, I'm not letting you do too much math because I ran out of time in the last class, and I don't want to run out of time with yours, but I do think you can divide two numbers in your calculator, right? You good with that? Okay. Now, let's talk about these next ones. These are called conditional probabilities. These are conditional probabilities. In other words, they have what we call a given condition. The given condition comes after that straight up and down bar, doesn't it? So it's asking, what's the probability that we select one person, that person is male, given that that person owns a pet? In other words, we're only going to consider the people that own pets. When you have a contingency table and a given condition, you only look at the given condition. In other words, get rid of the rest of the table. Where in my table are the ones that own pets? Well, it's a column, isn't it? Okay, don't use any numbers that are outside of that column because the given condition has just restricted what you can use to that particular condition. Given own a pet, I can only use theirs. Well, now which ones do I use? Well, that says they're male. Well, here they are. There's 63 of them. And it's over some total. I can't use 150. It's not in the given condition, is it? This time the total I use is 91. Do you understand? Are you good with that? If you watched the video, this is the second or third time you've heard it. Probably fourth or fifth because I think I said it several times. But it should be coming easier now. So I get 0.692 when I do that. Now let's look at this one. What's the probability that the person I select does not own a pet, given that the person is female? And get used to underlining that given condition, okay? Second condition, the given condition. We only want the females. Okay, I'm going to circle the group. Circle the group in your table that are female. There's only 3 numbers you're dealing with. Where are the females of the table? This time it's a row, isn't it? So I'm going to say how many are in this group that's the only thing I can look at. The other rest of the table may as well disappear. You cannot use it. Look at the no pets. Well, there's 32 of them. This time, what total do I use? 32 out of 60, right? So when I do that division, I come up with 0.533. Now remember, probability is always a decimal between the number 0 and 1, isn't it? It can be 0 and it can be 1, but it can't go higher than 1 and it can't be negative. Probability is just that way. Probability is always decimals. The only time we change it to percentages is if they tell us to represent it as a percent. If you do some of this division, though, and you get 3.6, you did something wrong, because 3.6 is not a legitimate probability. Okay? Are you with me? Yes? Okay, let's go on. Let's say that we're doing some random number selecting with a spinner, okay? Now this spinner has 12 numbers on it, so my first thought is, whatever I have, it's going to be out of the number 12, right? There are 12 possibilities on that spinner. And they're asking me, what's the probability that I will spin it one time, and I'll either get a 3 or a 5 or a 7? Well, out of the 12, how many are 3 or 5 or 7? Yeah, there's only 3 numbers that would fit that criteria, right? So I could easily reduce this. It's 1 over 4, which is 0.25. I don't even need a calculator to do it, right? Look at the second one. What's the probability that you get a multiple of 4? Well, you need to identify it, don't you? That would be the same as the probability of a 4, or what's another one that's a multiple of 4? 8? Or are there any more multiples of 4? 12. Anything else? That ends it, doesn't it? So we have the same thing. We've got 3 out of the 12, which is 0.25. Okay? Common sense, a lot of your probability questions are just common sense things. We're counting, we're saying out of the total, how many? Okay, and don't do the division. Don't go to decimals early. Go to the division at the end. Keep it as fractions as long as you can. All right, so now we've got this one. There are 172 physicians in Port St. Lucie. 64 female, 23 dermatologists, and of the 64 female physicians, 9 are dermatologists. Okay, that kind of loses me until I draw the picture. And that's what you do when they give you a bunch of stuff like that. You sort of put it down in a chart. Now, I always, when I'm making a chart, this is a contingency table, I always put male and female over here as rows. And whatever else they tell me, I put up there. Well, what are my choices? Well, I know that physicians could be dermatologists, or they could be not dermatologists. They didn't say anything else. They didn't say, you know, pediatricians or anything. They just said they're either dermatologists or they're not dermatologists, right? Or they didn't really say. So, and then I'm going to draw some lines because I really hate working with tables that don't have lines. And over here I'm going to say, well, this is my total. I guess I could draw one more line. And this is my total. And then I'm going to fill in the numbers that it told me. Maybe one more line. Okay. I'm going to fill in the numbers that it told me. It said there are 172 physicians, period. Okay, where does that number go? Anybody? Where am I going to put the 172? The total, isn't it? What I call the total. I mean, it's everybody. That goes in the corner, doesn't it? Okay, so we got that one. And of those, 64 are female and 23 are dermatologists. Okay, those are totals for total female. Well, here's the total female. And 23 are dermatologists. Well, where's the total dermatologist? Down here. We good so far? And then it gave us of the 64 female physicians, 9 are dermatologists. So we got to just look on this female row and find the female dermatologist. Now, if they give you that kind of combination, which really they have to give you 3 totals, and then they have to give you one interior cell that matches one of the totals, okay? If they give you that, you easily calculate the rest of them. You know how? Well, these two have to add up together to equal 23. So how do I get this top number? I say 23 minus 9. Well, that's 14. Well, these two down here have to add up to equal 172. How do I get the missing number? I say 172 minus 23. Well, that gives me 149. Are you following? I know I've already done it on the lecture, okay? So if I'm going fast and you haven't listened to it, it's going to feel really odd. Okay, now then I do the same thing here. I've got these two have to add to equal 64, so 64 minus 9, well, that would give me 55. And now I can keep going. I can say, well, 149 minus 55, 94. 172, I can just add them up. 14 plus 94, 108. At this point, I would double check myself. I would say, does 108 plus 64 add to equal 172? Does 23 plus 149 add to 172? It's a good idea to double check because there's no sense doing all these hard combinations of problems if you got the beginning numbers wrong, okay? But I think that's right. Now, let's answer the questions. What's the probability of female? Now, all they said was one thing. This is a marginal probability, right? Marginal because they only mentioned one thing. Where are my answers going to be? In the totals, in the margins. Probability of female, and guys, every time you do probability, it is a fraction, okay? It's always a number between 0 and 1. It is a fraction. It could be 1, so it could be 1 over 1. It can be 0. It could be 0 divided by something, right? But still, it's going to be represented as a fraction. Out of this total, because it's marginal, how many are female? Well, there's the 64. When you do the math, we're going to 3 decimal places. You should get 0.372. All right, let's now look at a conditional probability, okay? A conditional, underline the given condition. That's all you get to look at. Pick your numbers that are female given they are already, you know they're you're only choosing from the dermatologist. What 2 numbers do you use? Yes. Yep. Total dermatologists, down here it's 23. How many of those are female? Right there it's 9. How would you have done this? You would have restricted your table to just the given condition. Circle it if you need to. Those are the only ones you get to use, okay? And it clears it up for you most of the time. Now it asks an interesting question. It says, are the events, and it's always considered an event in statistics, even though it's a, okay, but it's only the person's, chosen profession. That doesn't sound like an active event. It's not, the definition of an event is different for us, okay, in stat. An event is whatever we define as the condition, as the situation that we're interested in. And we're interested in how many of them are female and dermatologists. Are those independent? Are those particular events independent? In other words, they're asking this question. Does it matter in Port St. Lucie, out of this 172 physicians that were surveyed, did it matter if they were male or female? Did it matter what career they chose? Did more females go into dermatology, or did more males go into dermatology, or did it not matter? Did they equally choose the field of dermatology, and it didn't matter whether they were male or female? Do you understand the question? Why would we ask it? Well, if you're selling something, and medical school might be considered a sales to some people, you need to know your population and what kind of things they go for. You need to know your market, don't you? And quite often, if you're selling something like on the internet, if you guys go into any kind of business, if you go into any kind of marketing, it matters. In many cases, you'll find out that in your particular population that you're selling to, that certain things make them make the decision to buy certain, they may choose what they buy based on whether they live in a certain type of house or not, based on whether they own pets or not, based on whether they are male or female or not. It just matters. It makes a difference. How do you tell, though? How do you know it truly makes a difference? Well, there's a numerical check for it. Now listen, the numerical check says, in this population, in this sample, in this survey of 172, did it matter or not? We can't say for the world at large. We can only speak about the 172 that we have surveyed, okay? So I'm not making a general statement about, yep, it matters or it doesn't matter if you're male or female, you will go into dermatology. That's not the statement. The statement is, in Port St. Lucie, out of these 172 physicians, numerically speaking, did it matter? Okay, and here's the check for it. This formula sheet needs to be your very best friend for the next 2 weeks, okay? Because look how many formulas you have to get used to in Chapter 3. And believe me, you're going to want to take it on the test, it'll be on your test, and you're going to want to check and double check that you're using the correct formula, okay? The only way that's going to work for you is if you get familiar with what they're called and where they are. So when I'm looking for independence, I kind of go, okay, where is there it is, condition for independence. You see it? And it says the probability of A is equal to the probability of A given B. It's a marginal is equal to a conditional. Now, it says A and B, and it's simply, this other version of it over here is simply written the other way to tell you that it doesn't matter which event you choose as A and which you choose as B. As long as you're consistent with where they fit in the formula, it doesn't matter. So you can't go wrong with which one you choose to make A, okay? Probability of A equal to the probability of A given B. The check for independence is that they are independent if those are equal. If they are not equal, we say that the events are dependent on each other. Therefore, it does matter whether they were male or female, did make a difference in whether they chose dermatology or not, okay? So we got to look at it. We've already kind of done these. Let's make female event A and dermatology event B. It just fits my formula. And I just did it that way. I could have chosen to make female event B and dermatology event A. I could have gone the other way with it, but I would have had to switch some things. Now look, I would have had to do another calculation. So I want to know, is the probability of female equal to the probability of A given B, right? Female given dermatology. Now it just so happens that those are the calculations that we've already done here. But normally you wouldn't have already done these. You would have to do them. You'd have to say, what's the probability of female? Well, that probability is 64 over 172. And I'd say, what's the probability of female given dermatology? And we found that one already to be 9 over 23. Are they equal? There's no way to tell, is there, until you do the division. Well, since we've already done it, it makes it sort of easy. What we're comparing here is 0.372 to, I didn't do the division here, did I? What was this? 0.391 is what that is. 0.391. Are those equal? Not really. Far enough off for me to say nope. It failed the check for independence, therefore the events female and dermatology are dependent on each other. In other words, I could say safely it does make a difference. Male, female made a difference in how they picked their chosen profession, okay, as far as dermatology goes. You got to be careful. Statistics don't tell you everything that people sometimes say it's being, they sometimes read more into it than it's actually saying. This only says this for these 172 physicians in Port St. Lucie, okay? Not for the world at large. You got it? All right. Okay, we want to take this. Now, the contingency table is wonderful, and there's some shortcuts we can have, but sometimes you're not given a contingency table. Sometimes you are simply given the numbers, and you have to know where they fit in with the math and the equations. So we're given the probability of an event A, the probability of B, and we're given the probability of B given that A has already happened. Now look, check for independence is not that. It's the probability of A has to equal the probability of A given B, right? Not the same as B given A. Please note that, okay? Some formulas use it. Probability of A equals probability of A given B. That's our check for independence. But when we do other things, it uses probability of A and the probability of B given A. So you have to really pay attention to your formula sheets. I did tell you this chapter was confusing, didn't I? Okay, it is going to be confusing. Pay attention to your formula sheets. So now we're going to look down here. We're going to say, we want to know, suppose we have dependent events and independent events. I'm going to kind of group these two together here and talk about them just a second. We're assuming first that A and B are dependent events. The check has already been done. They're dependent on each other, okay? If the check has been done and they are dependent on each other, then what is the probability of the and condition? Now, an and condition, usually we multiply the probability of one times the probability of the other. Look, where am I finding that? Right here. But notice that it says this is the and, which gives you a multiplication rule if the events are independent. What do I do if the events are dependent on each other? Well, if the events are dependent on each other, I have to use the probability of one times the conditional probability of the other event. Do you understand it? Do you see how this is backwards from that independence check that I just gave you, right? It's different. This formula is different, and that's where you will mess up if you're not paying attention. So here I go. I'm going to say I want this one. I want probability of A and B is going to equal to the probability of A times the probability of B given A. And most of the time, I write that down. Probability of A and B is equal to the probability of, what did I say? A times the probability of B given that A is already happened. Check and see, do you have those numbers given to you? Anybody? Yep. So A is 0.15, and B given A is 0.26. And when I multiply those together, I get 0.039. Be sure you check my work later, because somebody may write me and say, you didn't do that one right. I think I got it, though. Next, that's if they're dependent. What if they were independent events? Independent events, it's simple, guys. Independent says just multiply the two probabilities together. Well, that's simple. 0.15 times 0.34 this time. Does it make a difference? Well, yeah, this one came out to be 0.051. Okay? So are you always going to have to do this mathematical check before you do these and probabilities? No, most of the time it's going to tell you that they're dependent or independent. Some of the time it's going to be common sense. You know, if I asked you, how many of you rode in a truck to school today, well, does the fact that one of your school classmates rode in a truck affect whether or not you rode in a truck? I mean, those are independent events, aren't they? It simply doesn't matter. I mean, so sometimes it's common sense that one can't affect the other one. But if it's not, you know, if it's things that might happen and we just don't know, then you have to do the check for independence unless they tell you it's dependent or independent, okay? They'll tell you to check, though. I mean, you're not going to have to just check everything. Let's take a look at these last two. Now, those were talking about and these are talking about the or. Now, the or condition, I sometimes think about this as add and this is multiplication, okay? The and condition, we multiply. But for or, we add the events. We add the probabilities together. Now, let's do down here where they're mutually exclusive. Now, think about mutually exclusive doesn't have a numerical check. Listen to me. Mutually exclusive is common sense. Mutually exclusive things do not happen together. You cannot be, at this very moment, you cannot be attending an 11 o'clock class on main campus and Pruitt campus at the same time. Can you? I mean, aren't those mutually exclusive? Okay, common sense check tells us we can't. You know, it can't be day and night at the same time. It can't be, there's all sorts of mutually exclusive things. But mutually non-exclusive things, you know, would be, can you be attending Pruitt campus and taking STA2023 at the same time? Yep, you can, right? Those would not be mutually exclusive. They can happen together. So you have to kind of look at the data that's given to you and ask the question, can they happen together? And remember this, just because it is possible, okay, just because, I'm tired of sitting, it is possible that they happen together does not mean that it is possible in the survey of the data that you are looking at. In other words, ask me if I like cake and ice cream, okay? Okay, I like them both. But what if I'm given a survey saying, do you like cake or ice cream? Pick one. They just became mutually exclusive. In other words, I wasn't allowed to choose both. Do you understand? That makes them mutually exclusive, even though it's entirely possible for us to like cake and ice cream together, right? And it's possible for us to even eat cake and ice cream together. So, and now it's almost 12 o'clock and I've gotten hungry. Okay. So let's look at the second one first, because mutually exclusive is easier, okay? It's easier. It's a simple one. We simply add the events together, the probabilities, because probability of A or B is equal to the probability of A plus the probability of B. That's the formula. Be sure you know where it is, okay? And it even says addition rule for mutually exclusive events. And you've got to know that that is, what you've got to know, guys, that this is for the or condition. For the or condition, we add. Maybe that's what we should say here. Or is add, and is multiply, okay? That's what you got to know. That's not in your formula sheet that you have to memorize. Okay, so I've got probability of A plus probability of B. That's going to give me a 0.15 plus a 0.34. I mean, I don't have anything to choose from this time, so I just add the numbers up and I get 0.49. Now let's do the hard one. The hard one says that I have to take, I've run out of room here, probability of A, and I add probability of B, but I've got some duplicates because some of these things did happen together, and those are the ones that met the condition both A and B. I have to subtract those out, okay? Probability of A and B. All right, well, look, I did calculate probability of A and B up here, didn't I? And it told me to assume dependent, so I'm going to go up here and use these dependent numbers on that one. And I'm going to say probability of A, 0.15, plus probability of B, 0.34, minus the probability of A and B for dependent events was over here, 0.039, right? Okay? Okay. Did I do the math on that one? I didn't. Let me do the numbers real quick so that you can go back later and check yourself, okay? So 0.15 plus 0.34 minus 0.039. That is what I said, right? I got 0.451. Oh, I did do it. Okay. Okay. Remember these. And multiply, or add, but There are exceptions. There are times when you're going to have to go back here, and there are two different rules for each one of those, okay? So it's not as simple as just multiply and add. All right, let's look at another contingency table up here, because we're going to look at how to do the contingency table. We looked at doing those combinations with just the numbers given to us, but what if we get a contingency table? Well, first thing we do is put the totals in. And your totals for this one are 68 and 36 and 104. And up here is 55 and 49. Whoops, I'm sorry, that should line up. Doesn't, but it should. And then we're going to look at our questions that it asks us, okay? First, it's saying one student selected at random, and we want to know what's the probability that this student is both female and off campus, right? Both female and off campus. Now normally I would say, well, are those events dependent or independent on each other? But I've been given a contingency table, and there's a shortcut to it. The contingency table shortcut for the and is you go and pick up the total down here. Okay, that's always going to be your denominator. And then you're going to say, where are the ones that are both of those conditions together? What number? What's the number I'm looking for? Female and off campus. How many students do I have that meet both of those? Look, it's right here, right? And that works for dependent or independent, okay? If you have a contingency table, you don't have to stress too much about whether they're dependent or independent, okay? For the and condition, for the multiplication addition, you don't really have to. We didn't have to multiply anything. We just picked the two numbers. And now all you got to do is the division. So all I got to say is 26, okay, clear that, is 26 divided by 104. And go to 3 decimal places. Well, it's 0.25. Is that right?
I've seen something like this.
Is that right? Okay. Okay, so now let's do another one. Male and on campus. Well, once again, we've got a contingency table. We know what the denominator is going to be. Only thing you got to decide is what meets both of those conditions, male and on campus. How many of those do you see? Well, this is easy, right? Isn't this easier than what we were doing a minute ago?
Yeah.
45 divided by 104. I'm going to go to 3 decimal places. I'm going to go 0.433. Everybody good with that?
Mm-hmm.
Okay, that took care of my and, didn't it? Mm-hmm. And then once again, because I got the contingency table, I used a shortcut. Instead of having to multiply, I just picked the number, put it over the total. If you picked them independently and you did the multiplication, you would see it works exactly the same way, okay? But a contingency table gives you this option. Now let's look at this one. This is an or, right? These two are actually or conditions. So normally we add those, but there's a problem. We have to look at, for the or, is this. It has an addition rule, but we have to say, are the events exclusive or non-exclusive? In other words, if they're not mutually exclusive, then you're going to have duplicates when you do our shortcut method that you have to subtract out. So here's what the formula says. The formula says take the probability of A, add the probability of B, and subtract the probability of A and B. Well, I'm going to write it down one time for you. That would be, I'll call off-campus A, and I'm going to call male B. It could have gone the other way. It doesn't matter. Probability of off-campus, I'll just put off. And then add to that the probability of male. And then subtract the probability of off and male. That's what I'm going to have to do if they're not mutually exclusive. And I can see very quickly that they're not. How do I do it? I say, well, are there any people in this table that are both of those things? Any off-campus males that you see? Well, right here, there are 10 of them. They're not mutually exclusive. So I'll be subtracting those out. Now, what's the easy way to do this?
Put it all over common denominator.
Exactly. Let's see if I can write it so that I leave room for the next problem. I'm going to write this as one big fraction over the common denominator, and I'm using my total, 104. And then I'm going to add two numbers, and subtract the third for the numerator, I'm going to say how many in this whole thing are off campus, right?
36.
What's the probability of off campus?
36.
There's 36 of them. It was this number, right?
Yep.
How many are male?
55.
It was that number. And how many are both?
10.
Now, why are we subtracting those? Because look, when I took this 36 and I added that 55, didn't those 10 get added twice?
Mm-hmm.
They were in both groups. So I got to subtract them out one time. So I'm going to say 36 plus 55 minus 10. And when I do that, I get 81, still over 104. And now I'm going to finally let you go get a decimal, okay? You can do this and go to decimals early, and you will lose every bit of precision and probably come up with the wrong answer because you'll be a little off, a little off, a little off. And plus, your math's a lot harder. So stay with the fractions until the final one, and then do the division. 81 divided by 104, I got 0.779. Are you good with that? Okay, let's look at this one. On campus or female, okay? Same thing, guys. You've just got, this is going to be 3 numbers over the total 104. Find the 3 numbers. I'm going to add the first 2, subtract the third one. You want on campus, total female, and then how many are both?
I got this one.
Good.
Yeah, this is rough.
I think I got that. Is that what you got?
Yeah.
Okay. Do you like having a contingency table to work with? I mean, it makes it sort of easy, doesn't it? Basic few rules. You can do shortcuts with it. Don't have to worry about dependent or independent. You do have to kind of worry about mutually exclusive or not if it's an or, okay? Okay. Let's take this one. Taking away your contingency table, can you do the problems if they just give you the details about the numbers, okay? So they're going to say the event AA is, says, okay, probability of AA. AA is the event that a randomly selected IRSC student has an AA, seeking an AA degree. Blech, I can't even talk today. And then PM is going to be that a randomly selected student is on pre-med track, and that they gave us the 2 numbers for those. Now I'm going to come out here and write them down because inside a problem it's really hard to see that stuff. Probability of AA is equal to 0.44. Probability of pre-med is equal to 0.27, and you should always write them down and come up with whatever makes you understand what you're dealing with. Pre-med, AA, or write out the words. So now the probability that a randomly selected student is an AA degree seeker, and underline them every time you see and or, okay? And on the degree track is 0.05. So that's the probability of AA and PM, okay? Both of them together has been given to me as, what is it, 0.05? Okay, now I've been given all that. They want to know the probability that a randomly selected IRSC student is an AA degree seeker or. Okay, what's the probability with or, okay? If they're not mutually exclusive events, we have to subtract out the duplicates, don't we? Is being an AA degree seeker mutually exclusive from being on the pre-med track? Can you be both? Yes. So we got to subtract out the duplicates. What are the duplicates? Being both AA and pre-med. Well, they gave us that one. So they made it really easy for us. What are they saying? They're saying take the probability of AA, add the probability of pre-med, that's A plus B, right? And then subtract out the probability that they happen together. And when I do that, I see all the numbers are just right there for me, okay? So what is it saying? 0.44 plus 0.27 minus 0.05. How you doing? How many of you are going back and listening to Chapter 3 lecture one more time, do you think? Yeah, it's always a good idea after this. I'm just saying, guys, Chapter 3 is the hardest. Well, it's not hard. It's just confusing. There's just too many different variables. And then I will see you Sunday night in my open office hours, okay? Okay, let's go to page 4. Here we have a class of 32 students. 12 are dual enrolled, 20 are not dual enrolled. And we're going to choose 2 students randomly from this class, and here's really important words for us: without replacement. Now think about it. I've got a list of students, right? Or I've got their names on pieces of paper, and they put them in the big box on my desk, and I'm selecting the names out of the box. And I'm going to select 2 names, but the first I'm going to select and put it on my desk, and I'm not putting it back, okay? That's without replacement. Okay, so now, what's the probability that both of them are dual enrolled? Well, what are they really asking you? They're asking you the probability that the first is dual enrolled and the second is dual enrolled, right? Don't they both have to be true for both of them to be dual enrolled? First is dual enrolled and the second is dual enrolled. Well, when I have an and probability, I multiply, don't I? Okay, so I'm going to find these 2 probabilities, write them as fractions, and multiply them together. Okay, so first time I select out of this box of 32, I've got how many possibilities of dual enrollment? It's out of 32, right? 12 of them are dual enrollment, so that's my probability for my first selection. That's easy. So far, so good? Okay, next time, I didn't put the one I chose back, I put it on the desk. How many am I selecting from?
20.
Yeah, took one out, didn't I? How many of the ones that are still in there are dual enrollment this time? Because I took one of those out too. Now, it asked it, this time I subtracted from both of these numbers, but beware, you don't always do that. You know, I could have been looking for something else. And the second one would have been, you know, the number 20 or something, okay? All right, now all I have to do is multiplication of fractions. Now, you know how to multiply fractions. I know you hate fractions. I've heard it so many times. What do I do? It multiply numerator times numerator. So I got 12 times 11, and I get 132. And denominator times denominator, 32 times 31, and I get 992. And now do your division, and you'll come up with, okay, 0.133, I think. I think that's right. Okay? When you divide, I can do it. It's not 999, it's 992. I said it and wrote it wrong. Okay? Hate it when I do that. This is 992. Okay? Okay, next. What's the probability the first student is dual enrolled and the second student is not? Okay, so that's the probability, same thing, multiplication, right? First time, dual enrollment, same thing, 12 out of 32. Second time, how many students am I selecting from? 31. And how many are not dual enrolled that are still left in the pot? All 20. So we got 12 times 20. Boy, I did it wrong in the last class. I hate when I do that and then I find it later. Okay, so I got 12 times 20, which I didn't do the math on that one. That would be 240. And 32 times 31 is still going to be 992, isn't it? So I can divide by 992, and I come up with 0.24, and I'm going to go 2 with that one, okay? Okay. How are we? Good? Okay. Now we got a random sample of 375 students and professors. They're asked about their political party affiliation, and they were given only 3 choices. They could not say undecided, could they? They had to choose one of these. So this is 3 different choices instead of 2. Still, guys, it's a contingency table. So we put totals, and I'll give them to you because I'm in a hurry. I always underestimate how much time it's going to take to do these lessons. Okay, but that should help, right? All right, now we got some questions to answer. And I'm kind of grouping them together. I'm looking at my questions and I'm going, okay, these are and questions, aren't they? And these are or questions. And then that one is an and. So they're sort of different. I'm going to just come out here and write and multiply, right? Or, that's my addition rule. And this is an and. It's a multiplication rule. And that way, when I go to look in my formula sheet, I go multiplication rule, addition rule, right? So I kind of know where I'm headed with these, okay? This part you have to just memorize. It's not there for you to know. All right, so next I'm going to say this is probability that one student is selected, one person is selected, and it's both a student and independent, okay? Now, because it's contingency, I don't have to worry about these ands being dependent, independent, okay, of each other, events. So I'm going to say a student that's independent, I'm going to write it over this 375, right? And I'm looking for what satisfies both of those conditions. Well, I see 51 of them up here, student and independent. So all I have to do is the math, and I should come up with 0.136. And somebody correct me if you find I've done something wrong, okay? Next, what's the probability that that person we selected was Republican and a professor? Well, still, shortcut, right? Contingency table shortcut. Put it over the total, and find what meets both Republican, what was it, Republican and professor? 81. And do the division and round to 3 decimal places, okay? And now let's look at the ors. What's the probability that they are Democrat or professor? And you do have to ask yourself, are those mutually exclusive or not? Can you be both Democratic and a professor? Yes. So we will have to subtract out those duplicates. So in other words, I'll have to use my long formula or my long fraction. 375 is the denominator. I'll add the first 2 numbers and subtract the third. Okay? So what are the first 2 numbers? Well, how many total Democrats do I have?
123.
I got 123 of them. How many total professors do I have? 203. How many do I have that are both Democrat and professor?
63.
Yep, there they are, right? Democrat, professors. So you do the math in the numerator, add those 2 numbers, subtract the third, and then you'll come up with 263 over 375, and you'll do the division, round to 3 decimal places, and you should come out with 0.701. Okay, the second or, Democrat or independent. Now you have to ask yourself, are those mutually exclusive? Do you see anybody up there that can be both Democrat and independent? Find me a number that represents both of them.
The total.
Well, I mean, it has to be a number that's inside the cells, okay? That is representative of both of them. And there's not any. They're mutually exclusive. That's how we know. You can't be both Democrat and independent. You had to choose one of these columns, didn't you, when you were filling out the survey? So we don't have to subtract the duplicates this time. We simply add the Democrats and the independents, and then we do the division. Okay? And then the final question. I've got Republicans and independent. Well, do you see anybody up there who's both Republican and independent? That survey did not allow it, did it? So it's the joint probability of mutually independent events is what mutually exclusive events is what that is. What is it always? 0. And ask yourself, this is the way you should think about it. What's the probability that something that cannot happen together does happen together? Well, I just said it cannot happen together, right? These two things cannot happen together. Republican and independent, they can't be and, they can't happen together. So the probability of them both being there together is impossible, always 0, okay? Okay? Check that out and see what you find, but that should help you, okay? All right, now let's do some counting. There's a field in mathematics called combinatorics. If you want to go into math and you like to count things, and it's you can get degrees and you can get graduate degrees in combinatorics, okay? So, or concentration in combinatoric mathematics, and all it is how do we count things, and okay, it gets a little more complicated, but it is basically, this is your first step in combinatorics mathematics, is counting things. And one thing we always think about is this: each decision you have to make is a stage, it's a step. So when we're saying, they give you a thing that says, well, this restaurant, Underground, sells sandwiches, and they offer 3 choices of bread, 5 types of meat, 4 types of cheese, 6 vegetables, offerings. How many combinations of those things can you come up with? Well, what you think about is this. Stage 1, choose from the 3 breads. How many choices do you have? 3. Stage 2, choose from the how many meat toppings? Well, I got 5. Well, I'm going to end up multiplying all these together. Stage 3 is choose the cheese. Well, there's 4 possibilities. And stage 4 is choose the veggies. Well, there's 6. Well, that is how many possible combinations you got. You simply multiply the numbers together. If you say 3 times 4 times 3 times 5 times 4 times 6, you have 360 different possibilities. So now, knowing what I just said, look at the second problem. It says that a boy has 3 pairs of pants, 7 shirts, 2 ties, and 5 jackets. How many different clothing outfits can he come up with? Well, his first step, stage 1, pants, right? Stage 2, shirts. Same thing. You just have to make it be a step. Each decision he makes is a stage. And it's simple. Easier than probability, right?
Yeah, absolutely.
Yeah. All right, now let's talk about combinations and permutations. If we have a group of things and we're selecting, we want to know how many of them, how many different groups you can put together. Like I have this class, and if I was gonna put you into groups of 3 in this class, I would say, well, how many different groups, different combinations could I come up with if I was just grouping you in groups of 3? And let's say I had 35 students. That would be a combination, because I didn't say any order to the thing. I didn't give you any other directions, just how many groups can I come up with? That's a combination. Now, your calculator, even if it's just a plain scientific non-graphing, has a combination function on it. I almost guarantee you it does. And you're probably going to want to find that. Otherwise, you're going to be using the formula that's in here, and the formula has factorials in it, okay, which you also can find on your calculator. But that's your combination formula. I'm not going over it here because I want to show you calculator features. So what I've got is 11 members on the council, and at the recent meeting, 7 voted in favor of a budget increase. How many possible groups was that? I mean, we don't know who voted, but let's say it's a combination of, out of 11 people, we select them 7 at a time in groups of 7, okay? Now, when you do the combination, it's always combination, it's n combination x. And n is always the biggest number, so you're going to list the biggest number first. Now, try your calculator with me. If you have a TI-84 or an 83 or any TI calculator, probably what you're going to have to do, I mean, mine is one of those, okay, mine does it for me.
Yeah, you have to enter the number and then go and hit the function
Exactly. You're going to have to enter, you're probably going to have to enter that first number first, the 11, and then go find the combination. So what I think that's going to happen with you, it doesn't with me. What I do is I go to the combination, which is in the math menu. See the math button on your calculator, and then you go over to the probability features, okay? And on the probability features, you'll see this NCR. Okay, just pretend the R is an X, all right? The formula you have says NCX. Okay, so I'm going to choose number 3. And see, for me, it gives this cute little menu. I get to plug in the blocks. But for you, you probably had to put the 11 in there first, then hit math, probability, NCR, and it would ask you for the 7 then. And you just put the 7 in. Okay, when you have it looking like that, you just hit enter, and it tells you how many. We have a combination of 330 possibilities. All right? Now, like I said, even my little simple calculators up here, I think I have one, don't have one, even my simple calculators seem to have the NCR button, okay? Might be down yeah, there is one. Let's see if I can find it. I'm running out of time. Look above the number 8. You see it? You might have to figure out how it works on your calculator, but it's there usually. So don't try, practice so that you know that the numbers you're getting, that you're doing it right, because it's not going to help you. It's going to be very unforgiving if you don't fill it in correctly or use it correctly. Okay, so now let's look at this one. Kendra owns 4 books. She wants to know how many different orders she can place them in on the top shelf. Well, order of the books does matter in this case, right? Because that's what she's doing. Now listen, think about this one. I think I said this in the video, but you know how you have a combination lock and it has, I always think a combination lock really should be called a permutation lock, because the order of the numbers is what you're trying to pick out, right? So anyway, this one is how many different orders, and we know we're going to deal with permutation this time. How many are we choosing from? 4. How many are we going to choose at a time? Well, actually all 4 of them. You know, we're going to order all 4 of those books. How many different ways can we do that? Now, once again, if you've got this calculator or the TI systems, you're probably going to want to put in the number 4 first, and then you're going to want to go to math, probability, and choose NPR, which is the second one. So I'm going to enter 4 and 4. When you get it looking like this, after you get NPR entered, you enter the number 4, okay? And then you hit enter. And there's how many she can come up with. There are 20 different ways to place those 24 different ways to place those books on the bookshelf. Okay? Now let's take a look at this one. We have a total of 19 horses in a race. And how many different ways can the top 5 positions be arranged? Not selected, arranged. You know, it's not saying how many groups of 5 can we choose from 19. It's saying how can we order these top 5? Okay, so this would be if you were like betting on the horses. How many possibilities are there for them to come out in 1st, 2nd, 3rd, 4th, and 5th? So this is a permutation. Out of 19, there will be 5 top numbers. Find me the number, okay? Find the number. Doesn't help when you do that. Once you get that in your calculator and you hit enter, I got a possibility of 1,395,360. Do you understand why betting on the horses is not in your favor? Okay? Okay. Are you good with combinations and permutations? Okay. If it mentions order at all, it's a permutation, okay? All right, let's take a look and just see if we can do a little bit of work with your calculator, because these factorials are something that you need to know how to work, and the factorial thing is on these simple calculators also. Where? I don't know. I know it's here, I just don't know where it is. I have to find it. So for the graphing calculators, it's going to be also under math, and you're going to find all this stuff under probability, okay? And the little exclamation point, that is the factorial. Now, even on mine, I have to put the number in first. So let me clear this. And I'm going to say I have 9, and then I'm going to go math, probability. I'm going to select 4 because I want that little exclamation, and it places it. It puts the factorial exclamation point there, and then I hit enter, and it tells me what 9 factorial is. Now you listen to the video so you know what I'm talking about. 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 1, right? All the way down, okay? You can do that in a calculator if you want to, but if somebody asks you for 256 factorial, you're going to be sitting there a long time. 10 factorial would be the same type of thing. We say math, we say 10, and then we go math, go over to probability, and put in that little factorial button, and then hit enter. And 10 factorial came up to be 362,880. Really just multiplied it. What am I doing wrong? 8880, sorry. Right? That's not a comma, that is. I'm still doing it wrong, guys. 2 zeros, right? Better. It just multiplied it times 10. All right, next, I've got 10 minus 9 factorial, which is going to be, really do the math inside. This is 1 factorial. Well, what is 1 factorial, right? 1 times, and over here I've got 10 factorial times 8 factorial times 10 minus 8, which is 2. So I'm going to rewrite it. It's 10 factorial times 8 factorial times 2 factorial. And when I try to put it in my calculator, I have to do put in the number, go to the probability menu, and choose factorial button, put in another number, go to the probability menu, and choose the factorial button again, put in the number, keep doing it. I can what? What I want you to do is look at this number for me and tell me, how are you going to round that to 3 decimal places? The issue is, I think that's what you said. I'm having trouble hearing with mask. That's it. It's this number, but that E11 says, it's really scientific notation. It's multiplied times 10 to the power of 11. So look for that to happen. And look for also, sometimes it'll go the other way. It'll be 10 to the power of negative 15. We'll get to that when we get to the last test, okay? Or something like that. So it can be either way. It says move the decimal 10 places in positive direction, or if it was a negative, it would say move the decimal 10 places in a negative direction, or 11, whatever the number is, okay? You understand? So anyway, it's not a 2.9626, but that would be a hard number to write down, actually. Let's look at this one. I guess I'm going to just let you do some of these and find combinations and permutations. I'll plug the answers in up here so you can check your work. Okay, if you don't have your calculator and you want to come back, this is on your video. Fast forward until you get to that page, okay? But there's, I think, the answers to them. Now let's look at this last one, because this problem is once again giving us words instead of a contingency table, and we've got to be able to identify some things in it. It's asking, it tells us the probability of a student being an athlete is 0.16. Probability of a student being a biology major is 0.12, and the probability that they are both is 0.09. First thing I would like to do is come over here and write it down, okay? So I'm going to say probability of an athlete is equal to 0.16. They told me that. They said probability of biology, I'll call it bio, is equal to 0.12. And the probability of both, probability of athlete and, and bio, is equal to 0.09. Okay? All right, so I got everything out of that one. And then it says, determine the probability that a randomly selected IRSC student is a biology major given that the student is an athlete. They even wrote it down for me. Probability of biology given athlete, okay? So I know that if I call this event A and this event B, I can go and say the probability of athlete given biology, I can go and use something called Bayes' theorem for conditional probability. Probability of A given B. It's always going to be the probability of both of them happening together divided by the probability of the given event. Doesn't matter which one I call A and which one I call B. It has to be divided by the probability of the given event. You with me? So what I have to say is it has to be equal to the probability of bio and athlete. That's both of them happening together, divided by the probability of which one is the given one? Well, it's athlete. Now, let's see what they gave us. We don't have a contingency table. Did they give us the probability of biology and athlete happening together? Okay, they gave it to us as athlete and biology, but isn't that the same thing? You know, it's still both of them happening together, so that's going to be 0.09. Did they give us the probability of athlete? So that's all I have to do. And then I do the math and come up with 0.563. Okay? Now let's redo it. What's the probability of athlete given biology? Well, according to Bayes' theorem, conditional probability, it's the probability of both of them divided by the probability of the given. This time the given is biology. Well, once again, athlete and biology was 0.09, wasn't it? Just biology, 0.12. Which one is the given condition does really make a difference in your answers, okay? Go back to your formulas and make sure you can find every formula we use today, okay? I mean, you know where they are. You know if you get a problem like that on the test, you know where to go and look it up. Don't guess on these formulas because they're really close and they're really confusing, okay? Now, guys, I told you before, and I'll tell you again, we cover Chapter 4 next week, and it is binomials. So be familiar when you walk in the door, okay? And bring your binomial table because we're going to do some binomial lookups. So it's inside your guided notes book. Have it with you, okay? And I will see you next week.